All right, so welcome everybody to the final session for our first Hackaday Ghidra course. And so today what we're going to go over are some more, I won't call them advanced features, but just some Ghidra features we haven't touched on yet, some of the internals of how Ghidra works. We've gotten a lot of questions about how the decompiler works and things like that. So we're going to get into some of that today, and hopefully everybody enjoys it. So let's get started. So today we're going to go over a handful of additional Ghidra features that people have asked about in class and things that I think you'll find useful as you either revisit these exercises or look at later exercises in the future. So we're going to talk about loading external libraries. We're going to talk about patch analysis and diffing. We're going to take a look at some of the other interesting features Ghidra has, like the checksum generation. We'll take a look at how to manage memory maps. For those of you that have been watching the office hours, we've done a lot of that with some of the embedded firmware images we've been looking at. And then we're going to talk about, Ghidra extensions and writing scripts, and we'll walk through how to integrate Eclipse with Ghidra so that you can develop your own Python and Java extensions for it as well. And then we'll just do like a nice little wrap up where people can ask any additional questions they might have and things like that. So again, quick admin like we do every time. This is going to be our final session for now. So feedback and thoughts on the course are highly appreciated for everybody involved. And so the other thing that we'd like to add is I'm working on a Google form for the course for everybody to fill out if they want to, where they can provide kind of more in-depth information about the course. So you can send the feedback to either super conference. Okay, yeah, great. Give me 1 second. I'm actually going to shut this door behind me because of the light. Excuse me. All right, apologies for that, everybody. So office hours are going to be Thursday at 6, just like usual. And then again, so any questions you have, feel free to toss them at me through the HackadayU chat room. My username is wrongbod, or the super conference at HackadayU. And like I said, I'm putting together a Google form for everybody to fill out if they would like to, and we'll get that to you as well this week. So again, today, just to kind of give you another overview of what we're going to be doing, our final session for this first part here is we'll talk about patch analysis, the memory manager, extension via scripting, and we're going to dig into PCODE, which is the intermediate representation of assembly language that we've talked about in office hours here and there. And so we'll walk through, how to set all this stuff up, how to set up a dev environment and things like that to kind of give you those initial tools that you would need if you wanted to take things further and start, scripting and automating and just getting deeper into Ghidra's internals. And so with that, the first thing we're going to talk about today is loading external libraries. So some of you may have looked at the ELF exercise from the first session, where we had two different ELF files. One of them loaded the other and called a function within it. And so you can do this with Ghidra. So you can, when you're analyzing a binary, if you see that it calls an external library that has some kind of function, you can have Ghidra load that library on import. And then when you're analyzing that binary, you can actually navigate to that function in the other shared object and take a look at that as the as the decompiled output. And so this can help with auto analysis because sometimes it can help generate better type recognition and also assist with the function prototype generation. So I know we've talked about before, some folks were wondering, why sometimes the function prototypes are wrong and things like that. And it's because a lot of guesses have to be made when that it takes place in order for it to be more generalized. But if you can provide those other functions that are being called, you can kind of assist the decompiler with generating those function prototypes and just general type recognition as well. So we'll take a look at that real quick and how we might do that using the ELF example from session 1 kind of as a springboard for that. So here you can see this window that most of you are probably very familiar with by now. Right, we're looking at kind of the summary of importing the Legolas file, okay? And so if we look underneath in additional information, we can see that these two libraries were not found. And libc.so.6, you've seen that for every binary that we've analyzed so far, because they've all been linked with libc. But with this one, you're also looking for this libdabi.so, this additional library. And so Ghidra can tell us that, hey, there were 3 external symbols that I actually couldn't find. And so we're going to walk through how to point Ghidra to those external binaries and analyze those as well. So when we're looking at this Legolas binary, this elf that we'd written, those of you that looked at it probably got to this point where we see that main calls puts and says you have my program headers, and then we call and this function called elf example. And this function elf example doesn't exist anywhere in the binary because it's being imported from the other shared object. And so in order to, at load time, when we load this into Ghidra, in order to tell Ghidra, hey, I know I have a place that I will point you to look for other shared objects that are used by this binary, you click options, and then that's going to bring up this options menu. And some of you probably saw some of this when we were working on the various firmware images and things in the office hour, where we changed the image base and things like that. But what we're going to do for this, because we're trying to load an additional library, we're going to click the checkbox for load external libraries, and then we're going to click edit paths. And then that's going to bring up this window of all the paths that it uses to look for some of these shared objects. So I am on a Windows machine analyzing Linux binary, so it wasn't able to find libc.so, right? Now, if I were on a Linux machine, maybe it would have been able to find that, but it wasn't able to. And it also certainly wasn't able to find libdabi.so, because that's not a standard binary that's included. So in order to add that folder, you just click on this plus sign here, and that's going to bring you to a file navigation window here. And so what you're going to do is just point it to the directory that contains the additional elf files that you want to analyze. So you do that and click OK. And then here now we can see, when we re-import Legolas with the new import definitions in place, that we found libdabi.so, and there's only 2 unresolved symbols, the ones that were previously from libc. So let's take a look at this. Let's see what this looks like now that we have imported this, additional binary. So it looks fairly similar, right? We've got the elf example function call here that we saw previously. And if we double click that, right, it's going to take us to the relevant PLT entry in the binary. And so we get here, and it's still not something we can analyze. We have bad data. But if we want to, we have the other shared object loaded, so we can tell Ghidra to open that for us and analyze it for us by opening up the imports window. And so those of you remember from session 1, we talked about the imports and exports window. And so here we can open up this imports window and find that function that we care about from libdabi.so. And then we can click go to external location. And so when we do that, it's actually going to import and analyze that shared object. And so it's going to look very similar. You're going to get this message that we've always gotten before. So libdabi.so has not been analyzed. Would you like to analyze it? And then when you click yes, it's going to import the binary and analyze it just like any other ELF file, because that's all these shared objects are, right? These are just standard ELF files. And so now that we've done that, you can see here we have this other tab with the libdabi.so. And so when we double click on this label right here, it's actually going to jump to it in the other function. And so when we do that, it jumps into the other function and it shows us right here, where all that function does is just call puts, bad elf, go back to your library. And so the purpose of this exercise originally was just to show those of you that were interested how to take a look at the ELF headers and figure out imports and exports, even though Ghidra lays those out for you in the imports and exports table. The point of that exercise was just for everybody to understand, okay, this ELF file loads this other one and calls this particular function from it. And so that's how you can set up Ghidra to do that for you when you're analyzing some of these binaries. So this would be useful if maybe you have a file system image from something that you're trying to look at, and there's a massive amount of proprietary shared objects that you need to analyze, not necessarily at once, but you want them to be available in case you need them. So you can jump to them in the external function, then analyze them and see what the code does, and then jump back. And then you can use that information, right, to better inform the decompiler and to better manage your function prototypes and things like that. And so with that, we're talking about looking at multiple binaries. We're talking about binaries that import other binaries. And so one thing I wanted to go over with everybody, that for those of you that are maybe watching these videos before doing all the exercises, is patch diffing. And that's something that Ghidra can do fairly well. So one of the other main features that Ghidra has that's super useful is Ghidra allows you to check in and check out changes to binaries in a project. We haven't really talked a whole lot about setting up a Ghidra server and setting up a collaborative RE environment, but that's something Ghidra is capable of doing. So similar to a Git workflow, when you log into a Ghidra server and pull down a project, you can check out the latest changes and apply those to your binary. And using that same functionality, Ghidra has a patch diffing feature that lets you track differences between two different binaries that are fairly similar and run various analysis scripts on top of that. And so the version tracking feature you can use to kind of track maybe like minor changes to a binary and things like that. And so we're going to show how to set that up with a simple example here. So we have this project where we have two files, patch and patch2. And these files are slightly different, but again, we're working from just the compiled binaries that we have here of patch1 and patch2. So, you can run diff and you can, diff the hex dumps if you want to see where things are different, but that's only going to get you so far, right? Obviously, they're going to be different. Header information is different, size is different, checksums are different, etc. So we can start the version tracking manager by clicking these little feet right next to the dragon here. And so that's going to bring up this version tracking wizard. And there's lots of fields in here. There's lots of different columns. There's all kinds of stuff here. And so what we're going to do is start up the version tracking wizard, which is a quick and easy way to kind of import two things to compare them against one another. And so to do that, we again click up here. And so what this is going to do is this is going to open up this version tracking wizard for us. And if you want to start it up in a new session, you can. It's going to load this into the same project folder that you were working in before. And so what we're going to do is we're going to load a source and a destination program. So the source is going to be our baseline, and the destination program is what we're going to be comparing everything against. And so those of you that have already done all the exercises, you're probably realizing that this feature would be pretty useful, especially for all the exercises in session 3, because all the ones in session 3 are kind of built off of the same core code base. And so if you want to go back as a test to see what changed between the two, I'd highly recommend using this as a way to get more familiar with the patch diffing. But let's actually see what it looks like, right? So we add those two binaries, and then it asks for our source program, so we tell it patch. We'll do the same thing for patch2. And so now we have our source binary, which is just patch, and our destination binary, which is patch2. And so when we click next, it's going to bring us up to this precondition checklist. So this just goes through and makes sure that all the conditions are met so that it can actually run the various patch analyses on it. So what you're going to do here is click run precondition checks. Okay, great. So in this case, they all passed. And then we click next, and then you're just going to click finish. And what happens when you click finish is it will open up two separate code browsers. And you'll see we have one for source tool on the left. I apologize if the font is fairly small and you can't see, but the code browser for source tool is on the left, and the one for destination tool is on the right. And so you also see, if you look in this bottom right-hand corner here of each one, we have the version tracking match window there, which can be used to kind of synchronize between the two windows. But you'll notice that there's nothing in here. That's because we didn't give it certain things to track. So if we go back into the version tracking wizard, we can add correlations to be tracked across these two different binaries, right? So we do that by clicking on the plus sign. And here we get all kinds of correlation algorithms. And so these are the ones that are, included. But if you, look for these in the Git repository, you could add your own if you had other correlations that you wanted to run. So let's say you wanted to try to compare, a specific set of symbols across two binaries or something like that. You could add your own correlation algorithm here, which is, a fun exercise to do if you haven't. And so what we're going to do is we're just going to select all of these. So we want it to tell us every kind of match. So if you look at these correlation algorithms, there's all kinds of them. You have exact data match, exact function bytes match, exact function instructions match. So this is going to do kind of a byte by byte comparison of these two binaries and gather all of this information for us. And so once we set up the correlations, we click next. And this is going to bring you into kind of an options window that you can use to set the various parameters for these algorithms that are going to run. And so if you're doing this, if you're comparing two fairly large programs, this might take some time. So this will let you set various things like how many instructions you want to match in a function before you spit out a proper function correlation match. So you can say, here we're saying, I want at least 10 instructions to match before I say it's okay. And here I want at least 10 mnemonic matches before we actually say that it's a match. So you can tweak these to meet whatever use case you have when you're setting up the patch diffing. And so from here we click next. And then again, there's more options that you can configure. We're not going to set any of these for this example. And then again, we click next. And so here it's telling us, all right, here's my source program, the destination program, here's everything, all the correlators we're going to run. And then finally, we click finish. And so it'll tell you right away, okay, there weren't any function reference matches or data reference matches, but there was plenty of other matches. So now our version tracking wizard looks like this. And we've got all kinds of different things that, some of these things match, some of them don't, some of them are similar, some of them are exact. And so if you look in the right column here, we have the algorithm column, and you can sort by that if you're looking for things that maybe are an exact match or a similar match, and you can sort them by clicking on whatever column. So maybe if you're only interested in, if you want to source by address and just start at the base of the executable and work your way down, you can do that. If you want to sort by confidence level, you can do that. And all of these variables are tweaked within the various correlation algorithms that you're using. So one difference here, right? We've selected the main function, and here in the two patch windows, we can see where some of these differences are. So again, just as a simple example, right? On the leftmost window, we can see that the version string is version 1, and here it's version 1.1. And then we can see that these constants are different. We have beef deed and beef face. And so these programs that we're looking at right now are fairly small, but you can see if you're looking at, a longer program that was maybe more complicated, this is a super useful feature that you can take advantage of for doing, patch diffing. And so this is just the way that it all looks in the version tracking wizard, but you also, again, you'll have the same thing now in the code browser for each of these ones, each for source and dest. And so when you click on an area, it'll populate the various algorithm matches that happened, within this function or near whatever you've recently clicked on. So that's pretty cool too. So if you just want to have this there to analyze as you're going through the binary, this is a fairly useful window to have, comparing it to, another patched binary or something similar. And so here is a difference, right? The Ghidra was able to determine, okay, well, you have the exact same symbol match here for this function. And then when we load it up, we can see that this is where they start to differ. So if you look at the bottom here, you'll see that the patch 2 actually added an additional add operation to this function as opposed to what patch 1 had. And so this just lets you kind of cut through everything and get right down to the bottom of, what has changed between these two binaries. And so that'll be super useful if you want to go back and look at what changed between the various exercises for session 3. I would recommend doing that to get a better handle on how to use this patch diffing tool. And so another simple way to check, whether two binaries are different or and things like that, there are, using checksums. So let's say you're looking at a firmware image or something, and maybe you've patched it and you want to quickly check all of the various checksums. Let's say you know that this image has a CRC32 and you've made your patches to it. You think you've fixed up the checksum appropriately and you just want to check that quickly. Well, Ghidra has, a built-in checksum tool that you can access. And on top of that, within that checksum tool, there's various transformations and operations you can apply to the checksum itself. Oh, I've got a raised hand. Do you want to type out your question? Whoever raised their hand. Okay, well, if you type out your question for the raised hand, I will get back to it at the end of the session today. So again, with the checksum generator, there's all kinds of options you can apply to the checksums, and to open that, you just click Window and then Checksum Generator. And some of you may have already seen this before. I just wanted to go through it because this is sometimes a useful tool if you're looking at firmware images or things from an embedded system. And so this is the checksum window. And so you can see here we've got all kinds of different checksums that it includes by default. You could of course add your own if you wanted to. And so within that we've got the ones complement. You can see here ones. You click that, you get the ones complement. And here you've got the twos complement. You can show it, in hexadecimal value, whatever. And so there's all kinds of ways you can print out and show the various, checksums for whatever program you're looking at. And that's just something that I wanted to cover really quickly because that's a feature that some of you may end up needing later on down the road. And probably what's more important for those of you that are interested in looking at embedded systems, because we've talked about this quite a bit during the office hour, it seems to be a fairly popular topic, is the memory manager. And so again, those of you that were around for the office hours saw that we use this to fix up the memory map for an embedded processor that we were looking at. And so the memory manager lets you add memory regions to Ghidra's baked-in memory map. Now, we haven't had to do that for the ELF files because all that information is already in the header, and Ghidra can do that. And so for each memory region that you might add to the memory map, you can set things like the start address, the end address, the memory permissions, whether it's read, write, or execute. And we kind of talked about this a little bit during office hour, is that the way you set permissions for these memory regions changes the way that the analysis is performed on it, right? So if Ghidra knows that it's only read or write, then it's not going to worry about anything that it might think it would be code in that region. And so you can also set up a memory region as like an overlay region, which would mean that it might overlap with another. And so let's take a look at how to open up the memory manager and utilize it. So from the Ghidra toolbar here, you select this little, looks like a little IC, and you click on that, and then it brings up the memory map. And so what we have here is half of the memory map for what's the Game Boy Advance memory map. But if you wanted to add a new region of memory to this, you would click on this plus sign, and that's going to bring up this. And so this is the window where you add all of the parameters for the memory region that you're trying to add into Ghidra. So again, we can set whether it's read, write, execute, volatile. You can set the name, you can give it a start address, length, etc. And so if you want to initialize that memory with a file, let's say you've grabbed a RAM dump from something and you want to toss it in there, you can do that. So you can set it with file bytes, you can set it to initialized or uninitialized. And then let's say we just fill that out with this test block region here. And we've set it to be RWX because it's extremely unsafe and we don't initialize it even better. And so now we can see that this test block region shows up here. And for those of you familiar with the Game Boy Advance, you probably realize that's actually where the BIOS would be in the GBA. And so when you're working with these memory regions, particularly if you're working on some embedded platform where you might have like JTAG access or something like that, you can add binary files to these regions. So if you get a RAM dump or if you get a dump of some values in a peripheral, maybe you can add that info to the program. And then if it's something that might be bank switched or referenced fairly regularly, and you want to still try to map out the entire memory region of whatever target you're looking at, you can set up memory regions as overlay blocks. And probably most importantly, and one of the more useful things about this, is you can instrument this through Ghidra's API. And so if you look at people that have written example loaders, there's the SVD loader for STM32 chips that's really good, and that utilizes this functionality to on the fly generate memory regions for whatever you're reverse engineering. And so with that, we've talked about some of the user-facing features that everybody can take advantage of if they're looking at, these exercises, if they're looking at, maybe a firmware image. Something I really wanted to get through with everybody here before we closed out this first chunk of the course is some of the more internal features of Ghidra and kind of how it works from the inside. And so we've gotten a lot of questions about the decompiler, we've gotten a lot of questions about the disassembler and things like that, and I wanted to just provide kind of a 10,000 foot view of how that stuff works. And so we've talked about, one of Ghidra's most powerful features being that it has this decompiler, right, that works with almost every processor that it supports. And so if you want to include a new processor, if you want to add support for a new processor, you're going to implement that in what's called SLEIGH. And we'll talk about that later on. But SLEIGH is the language that's used to define these processors. And what that defines is how we actually go from the raw bytes that we talked about back in session 1. Remember, we discussed how, going from raw bytes to assembly is disassembly. And then going from that to a higher level of something that looks like C that we're used to is, decompilation. And so the way Ghidra does that is we decode the bytes to assembly code via parameters that are outlined in SLEIGH files that we're going to talk about. And then that also generates what's called PCODE, which is an intermediate representation of how the assembly instructions work. And we'll get into what that looks like as well. And what you really need to take home about all this is that the PCODE is used across every processor. And the reason for that is so that the algorithms that generate the decompilation, can operate on PCODE instead of worrying about specifics for each particular processor. So no matter what the processor is, when it gets loaded and analyzed by Ghidra and PCODE gets generated, that PCODE language can almost be thought of as a language for modeling processor behavior. And the documentation for it in the Ghidra source is actually really good. So essentially, when something gets initially analyzed, we can have, two passes. When we have disassembly, and then we have PCODE. And those are both generated by what is in these SLEIGH files. So let's talk about those really quickly. So again, SLEIGH kind of specifies that translation from assembly language to PCODE. It also is what defines the parameters needed for disassembly as well. And so this is kind of, like we mentioned before, this is a language that's used to create these processor modules that then generates the immediate representation, or the IL, of the language that defines the processor behavior. And so there's some great examples for this in Ghidra processors. If you want a simple example, what I would recommend starting out with is something like the 6502. And for those of you that may or may not be familiar with the 6502, it's a 16-bit instruction set computer with, I think, less than, I don't know, it's not nearly as many instructions as some of the other CPUs that you might see. And this is what was used, in the NES, and I believe even in the SNES as well, an extended version of the 6502. And so when you look at this processor example and any processor example in the Ghidra source code, you're going to have 4 files: C-spec, the LDEFs, P-spec, and SLEIGH-spec. And so the C-spec is the compiler specification. That's what's going to define, how various compilers will handle things like, function prototypes and epilogues and prologues, like we talked about before. You've got the language definitions, which, will define things like endianness and things like that. The processor specification, which again kind of defines the various features of the chip. So you're talking about, memory maps and things like that. And then finally, the SLEIGH specification, which lays out how instructions are decoded and how PCODE is actually going to be generated. And so if we look at the language definition for the 6502, we can see that it defines a handful of fairly standard things, right? So we define the endianness, we define the size, processor size. We define various things like, where do you find the SLEIGH file for this, etc. And so we also point it to, you see here we point it to the processor spec, we point it to the compiler spec, things like that. And so you can see this one actually imports some manuals and some information from IDA, if you actually have that installed. And so, what does the processor spec look like? Well, so if you're familiar at all with 6502, these are various I/O ports. Okay, and so these I/O ports are just memory mapped registers for that particular CPU. So any, memory mapped register, or, maybe a reset vector interrupt handler that is going to be for a specific CPU is going to go in this PSpec file. And so don't confuse this with things. You don't necessarily want to confuse it with things like peripherals, like you might see, like a SPI controller or something like that. You can just add those as memory regions. You don't necessarily have to go to this level to add something like a SPI controller or a UART controller. And so another example of something that might be in a PSpec, again, is the memory blocks, but this is for that particular CPU, right? So the 6502 has like a dedicated stack space that we have laid out here, and I have another RAM region load out here as well. So next you're going to have, once you've gone through kind of the PSpec, the processor specifications, you're going to talk about, the different types of function prototypes that some code that have been written for this processor might use. And so for the 6502, which was largely handwritten in assembly, it's fairly straightforward, right? So we can see here the various parameters that are necessary for the function prototypes for 6502. And that's what's going to be defined in the CSpec, or the compiler specification, which, makes sense. It talks about calling conventions, stack growth, alignment, which we talked about with structs in session 3, and things like that. And so finally, the SLEIGH spec is going to be all these file formats are fairly complicated, which is why I wanted to use the 6502 as an example, because it's a relatively straightforward processor. And so this finally has things like instruction definitions, register definitions, things like that, defining various address spaces and what types they are. And so all of this data is what's going to eventually get fed into and utilized by the P code later, in a sense. So we're defining these registers that the P code is going to operate on, right? And so we have, we're defining the alignment. So, 1 byte aligned. We're defining the endianness, things like that. We're going through and telling it the address spaces that it can work through. And then we're mapping out all the various registers that 6502 has, which, as you can see, are not that many, right? So I think on our x86, we only have 4 here, and we're looking at, more than 32 on our regular x86 64-bit CPU. And so the SLEIGH spec, in addition to all this, where it's defining the registers, it's defining the address space, things like that, it also defines how the instructions are decoded. So very quick crash course in 6502 assembly, please don't fall asleep on me, is the instruction store A will store what is in register A at this operation, at this address. And so what we can see here is that we have the conditions that are needed for this assembly instruction. These both represent bit ranges in the actual instruction byte that are set, as well as the operand here. And then we have the resulting, P code underneath of it. And so what we do in this SLEIGH spec file is define all the parameters needed for disassembly. And then we also define up here how the instructions are going to be shown in the disassembly listing, which is fairly useful as well. If you ever want to try to modify things like that, you may have to modify things in the SLEIGH spec. And so this is this was kind of a very quick overview of how that works. And I wanted to go over it just so everyone kind of understands from a super high level how this stuff works and how it looks. And so we talked about, P code, and we talked about how the SLEIGH spec is used to generate P code. So let's talk about that. So P code is designed to, if you read the docs in the source, which I would highly recommend, it's designed to be capable of modeling, a general purpose processor. And so this language is a register transfer language. And it's used, like we talked about before, as kind of an abstraction layer for all the CPU specific stuff. So if you can analyze P code for, one processor, you can analyze it for another. And that's why the decompiler works across all these various processors, by operating on this immediate representation, or this IR, IL that you might hear people discuss. And so this is what's operated on to generate that decompiled code. But, what does all that look like, right? So if we're looking at an assembly listing, and again, this is 6502. This is, fairly simple assembly. So if we look at this instruction, load A3, what does that do? That loads the value 3 into register A. These are very straightforward instructions. And so now if we want to look at the P code, we click on this, I don't even know what you'd call it, these bricks here. Right, so you click on this, and what that's going to do is it's going to open up the editor for the assembly listing. And I believe we talked about this in session 1. So we open up this editor, and then we'll see here that an instruction/data P code is grayed out. And so if we right click that and enable the field, now for every instruction, we see 4, 5, 6 instructions. So when we read this as 6502 assembly, we're saying, all right, store the value in register A at this address, okay? But what does that look like when it gets translated into that intermediate representation of P code? Well, it says, all right, at this register in RAM, or at this location in RAM, at this value, we're going to store a copy of A. And then we're going to check the 0 flag, and we're going to check the less than 0 flag and set those in case they're necessary. So, when we're looking at things that branch, this is how you would set flags and things like that. So again, when we talk about what this instruction does, and we talk about flags that might get set when we do a compare, we kind of think of it as a linear process where, you just check these values and then you move on. And so the P code is the representation of kind of every single step that has to take place for one of these instructions to be performed, right? So it lays out, okay, you're moving this value from A into this address in RAM, and then we're checking these flags, and then we move on to the next instruction. And so P code is an even more granular way to look at these instructions than assembly a lot of the times. And again, the reason we use this is because this P code is the same, core concept, the same language that's used across all the various processors that Ghidra supports. And so let's really quick, just to make sure you've fallen asleep by now, let's take a look at, this P code from kind of a lower level. So again, we talked about what this instruction does is it stores the value in the A register at this address. And so we see that happening with this first one. And then we also see the flag checks that happen after the fact. And so first thing we do, right, at this value in RAM, we're storing 1 byte, and it's the copy of this register, or the copy of the value in that A register. Then we're checking the 0 flag, setting it if necessary, and then we're checking the less than 0 flag and checking that if necessary. And so with all that, what I would like for everybody to do is in the exercises folder, which hasn't been pushed yet, it'll be pushed later this evening, there's going to be 4 exercises that are all the same C code compiled for 4 different architectures. And they're going to be ELF files, so Ghidra will be able to tell you the architecture and you won't have to set that manually. But what I would just like for you to do is for each of them, take a look at the P code and think about how it's different, see if any parts of it are similar, and see if there are any patterns that you might see in the P code that gets generated. And so with that, we've talked about kind of from a very high level how Ghidra works internally. We've gone over a few features that we haven't really touched on before the end of this first sequence of classes. And so what I wanted to get through with everybody before we finally close out is kind of how to extend Ghidra via scripting. So we're going to talk about that now. So you can extend Ghidra via various plugins, right? You can write scripts, you can write loaders, you can write processor modules like we just talked about. And so you can do this with the Ghidra Dev plugin that is designed to be integrated with Eclipse. And this lets you write either Java or Python. And so you can kind of pick whichever one you want because the APIs between both of them are the same or as close to the same as they can be, right? And so if you want to install the Ghidra Dev plugin into Eclipse, I'm going to show you how to do that. So this example that we're going to walk through is me using the latest version of Eclipse pulled from the Eclipse website. And you go to Help and then Install New Software. And then this will pop up. And it's going to ask you where you want to install or what you want to install from. So we click Add. It'll bring up this menu. An archive, because we're grabbing an archive that's included with the repo when you pull it from Git. And then here it's going to parse that and let you select what you want. We want to select both of these things and click next. And so here it's going to tell you, all right, you're installing this Ghidra Dev plugin. Go through, accept the licenses, etc. And so now in our Eclipse window here, in our Eclipse toolbar, we have a little Ghidra Dev button here, which we can use to kind of integrate our Ghidra installation with Eclipse and use that for more verbose information when we start writing scripts and expanding on Ghidra's core capabilities. So the first thing we have to do, though, is we have to link our Ghidra installation with this instance of Eclipse. So click on Ghidra Dev and then link Ghidra, and it's going to tell you we don't know where Ghidra's installed. You need to tell us. So click on this plus sign and point it to your Ghidra install, which again is just what you would have pulled from ghidrasre.org. And so you select that folder and then click apply and close. And then now when you go under new, you're going to have options to create new Ghidra scripts and things like that. So we're just going to write a simple hello world script that's going to print a pop-up to the screen. And then we're going to go over some of the more simple APIs that people might find useful. Take a look at the Q&A real quick. Just the stock Java one. Yeah, so we got a question for which Eclipse build variant do you use? Just the stock Java one. Yeah, so just the Java IDE. So we're going to click Ghidra script. And then this is going to look like, if those of you that have used Eclipse before, this just looks like any other project manager, right? So we just call it example script, and the directory, you set that wherever you want it to be, and then we run it. And then you're going to get something like this. So you see here I have two. I have example script and Hackaday example. And so what you want to do is right click on home scripts, or you can do this in any of these included modules, but to make it easier, just right click home scripts and then go down to Ghidra Dev, new Ghidra script. And then that's going to ask you for, the name of your script, the language you want it to be in any of these categories. I would recommend filling out the category and just call it, example, or call it whatever you want so you can find it in the script manager later. And we're going to walk through what that looks like as well. So here we filled out the kind of example info for our script, click finish, and then we get like this nice little template. And so for our script, again, for now, all we're going to do is just pop up and say, hello, Hackaday. And so in order to run this, right, we've already linked it with our installation of Ghidra. So you're going to click on this arrow and it's going to ask you what you want to do. Do you want to run it as a regular, Ghidra app? Do you want to run it as Ghidra headless? And so we want to run this as a regular Ghidra app. If you were writing a script to do analysis on a bunch of binaries and you didn't care about interacting with the GUI, you would want to do that with Ghidra headless. So we're going to tell it to do it with just regular Ghidra, and what that's going to do is it's going to launch Ghidra for us. And so once you have that, you can open whatever target program you want to test the script on. So I opened up the Game Boy Advance ROM that we'd been looking at, and the next thing you want to do is click Window and then Script Manager, and that's going to bring up the script manager that you can use to edit and run scripts and add new folders to be run from here. And so ours was under the category Hackaday in the comments here. And so that's why it shows up under this folder. And I would recommend doing that even if you just put, your name here so it shows up here and it's easier to find, right? And you can also add things like key bindings, menu paths, and a toolbar image for it to show up if you want to just run it by clicking an image in the toolbar. And so you can fill out as much of this as you want to make it sort of easier to access. But the script manager is an important part of Ghidra as well, and it's something you should be familiar with to find, other examples of scripts that people have written. And so with that, we have our script. We see it right here. We see all the fields that we filled out. And then to run it, we're just going to click the play button up here. And when we do that, we get this little pop-up that says, hello, Hackaday. Very straightforward. But just wanted to walk you through. I actually had a hard time the very first time I wrote something finding how to actually run it from Ghidra. And you do it within the script manager, and without a category chosen, it's kind of difficult to find your particular script that you've written and that's in the Ghidra IDE. And so as you run this, any logging that you output or any information that you choose to print out to the console will show up, both in Ghidra and in Eclipse. And so you can set breakpoints, you can do things like that for loading your script and kind of debugging your script or processor module. And so the example that we looked at just a second ago, right, was Python, or was Java rather, and you can also write the stuff in Python. And if you want, you can use the PyDev plugin for Eclipse integration. Another really interesting feature and useful feature is the Python shell that's already built into Ghidra. And some of you may have already seen this. And so we're asking, do you have to restart Ghidra when you change the script in Eclipse? No, you don't have to do that. And that's very useful. So the Python interpreter utilizes the flat program API, which is kind of what we're going to focus on for the rest of the session, which is kind of the more standard API that you can use. And so that standard API provides lots of global variables for you and is a quick way to kind of get up and running with scripting with Ghidra. And so when you're running a program and using this flat API, Ghidra instantiates a handful of global variables for you that you can use while scripting, including current address, current highlight, current program, current selection, current location. And so all of these are relevant to your cursor location. So if you've clicked on a certain location or a certain address, that's the value that's going to be in current address. And so you'll see how we reference these globals later with some of the flat program API calls from the Python shell. And one of the more kind of important things to understand, or at least was the most difficult for me initially, was getting used to the concept of addresses being an object. So if you've written, IDA scripts and things like that, lots of times addresses can just be represented as, a regular integer. And so address objects are their own separate thing, and they have their own, subfunctions for, adding and subtracting and things like that. And you can also generate addresses easily using this address factory here down below. But one thing I just wanted to cover is that, these address objects are not necessarily integers. They are, additional objects in Ghidra, which makes sense when you think about it. It's just sometimes it's tricky to kind of wrap your head around that. So if you do, address plus equals something, sometimes that might not work the way you want it to. And so with these addresses, right, we can do things like if you want to create data, one of the things that we had to do before, right, we had to create data fields for these various structs. And so some flat program API calls that you can make would be things like create byte, create character, create dword, create ASCII string. And that will all operate on the address that you pass it, right? And so these are things that you probably would use more if you're looking at, say a firmware image or something that hasn't quite been flushed out by the analysis process, and you want to script through and create strings and pointers and things like that. But you can also use the flat program API to interact with instructions. So you can write programs to, parse the various instructions, get the mnemonics, get the operands. You could even get the PCODE representation of the instruction from a Ghidra script. And I wanted to show you what that might look like. So here we have an example program. For those of you that watched some of the office hours, again, this is just a function in this Game Boy ROM that we looked at. So this is all ARM here. And you'll see that we use the function getInstructionAt as part of the flat program API, and we use the current address global variable. And because our current address is 80000C0, it grabs this move instruction. And if we want to do something like get the number of operands, you can do inst.getNumOperands, it returns that, inst.getBytes if you want the raw bytes. And then we have, .getPCODE, which gives you the PCODE for the instruction. And so if you want to iterate over instructions, you can interact with functions, or you can call it get next instruction, which will grab you the next instruction in the given function. And so with the flat program API, not only can we can manipulate and modify instructions, data, we can also take a look at functions. So we can look at the function signature, we can look at the parameters, things like that. So let's say you wanted to clean up the function prototype or the function parameters, and you knew that something was consistently being calculated improperly. You could write a script to clean that up by manipulating those functions and modifying those functions. And again, you can create one simply by using, get function at address. There's also create function address. And so in this next window, we have a couple examples of what that might look like here, when with that same function, we say get function at current address, and it returns our init function. And so we can do things like get the entry point, get the name, get the return type. This is the init function, so it doesn't really return on the Game Boy, but if it did, you would be able to see what return values that it actually tries to return, or the types rather. And so that's just a really quick example of some of the function level calls that you can use within Ghidra's flat program API. And we talked about, generating P-code. We talked about grabbing instructions. So yeah, we can use this flat program API to get the P-code for the instruction. And so these P-code ops, this object that is returned from that, provide the P-code operations for the given instruction and, kind of describe what's happening. And then the really interesting thing is you can take these P-code ops and you can actually emulate them using Ghidra's P-code emulator. And that's something that's a super powerful tool that Ghidra has, is an emulator for that underlying P-code. And so if we want to look at how we might just, iterate over some of the P-code in a function, this is just a very simple example of, we have our same thing of, get instruction at, where we grab this instruction at this address, and then we call get.pcode and just iterate over the P-code functions that are actually called, or the P-code representation of that instruction. And so that is kind of how you can script with the P-code, the get P-code function using the flat program API. And so finally, to kind of wrap things up, we're getting close to the end here, and I wanted people to have a chance to ask any other questions that might be more generic, is the final exercises I pulled from CrackMe's.1 after solving them and kind of assessing the difficulty. And so these are not ones that I've written. These are ones that I have, we'll say, artisanally handpicked for you, that are in kind of an ascending order of difficulty. And I wanted to use this as an opportunity to introduce this site to everybody so they can use this to practice reversing in the future. And so this is a really fun site. You can go through and set parameters for what you want to learn how to take a look at and what you want to maybe understand better. And I used it a lot back when I was initially learning how to do RE, and it was very useful. And also we had some questions about the source code for the exercises. So we'll be reversing or releasing those after the office hours this week as well, so folks can take a look at that. And so to kind of close things out this evening, this is going to be our final session for now, and I wanted to thank everybody for showing up and participating. It was a lot of fun. And if you have any questions or commentary, prep that and let us know for the office hour.